Very good morning, students. This is Kar Kurli, Assistant Professor, Triple Department from RMD Engineering College.
Today we are going to discuss about performance parameters of short transmission line. Before that, we already know about the types of modeling of transmission line. So there are three types. One is short transmission line, medium transmission line and long transmission line. Based on their length and voltage level, we will be classifying. Then in short transmission line, 50 kilometer length of the transmission line and voltage level less than 20 kilovolt is modeled as short transmission line. Now the equivalent circuit in short transmission line have only the resistance and reactance, inductive reactance. Here the capacitance effects are neglected actually. So see here, in this is a phase conductor and another one is neutral conductor. In both a capacitance existence between these two conductors are negligible in short transmission line. Hence capacitance effects is not included here. So these two are in series with the load, so we can combine this as R and X. This is the equivalent circuit, correct? R and X only. And this end is the sending end voltage, another end is the load end is the receiving end voltage. So we will be writing its equivalent KVL equation and KCL equation. Now see here we are having a R and X only, no shunt path. So we can say in this loop IS here at the receiving end side and sending inside IS and receiving inside as IR, correct? See, there is no shunt path, so IS is equal to IR in this loop, and R is the loop resistance, as I already told you, combining the resistance of both conductors. Similarly, reactance is loop reactance of the lines which combines the reactance of two lines. So single phase line is having phase as well as neutral, no? So there are two wires or two lines, we can say like that. The series impedance is now given by Z is equal to R plus JX, and the voltage equations applying the KVL loop equation. What is the loop equation? The source is or potential raise is Vs. Based on the circuit, potential raise is Vs. So Vs is equal to, so the flow of current through this series impedance is Is multiplied by, we can say this either as Z or what is the element impedance here you are having, R plus Jx, correct? This is your impedance Iz. Iz is a drop, okay? Then plus voltage across the load terminal, which is considered to be the receiving end voltage, correct? So VR. In order to avoid the confusion with this R for the representation of receiving end, no, I am using this lowercase r. Okay, it's up to you whether you can use lowercase or uppercase, but it should be in suffix. Okay, so Vs is equal to Is R plus Jx plus Vr. And one more equation, current equation is 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 equal to IR. These two equations are very important. With the help of this equation, first equation, no, we are going to draw a phasor diagram. From the phasor diagram, we are going to derive efficiency of the transmission line as well as voltage regulation of the transmission line. See here, a phasor diagram. Okay, this is the equivalent circuit which we have already discussed. In this phasor diagram, we will take VR as the reference phase. This is your VR. I is the reference phase here. I is the reference phase. Okay. Then VR is receiving end voltage will be leading, which is nothing but current is lagging. Correct. We know it is having inductive reactance. It is not pure inductive reactance. If it is a purely inductive reactance means current, this is the voltage, correct, and current will lag exactly by 90 degree if it is a pure inductance. But it is not a pure inductance, it includes resistance, so it it will not lag exactly 90 degree, correct? Now I have taken I as reference. I will be lagging. What does it mean? So voltage is leading. So voltage is leading. This is my I, correct? And then this is the voltage line. Now which is nothing but VR, correct? VR. Now this term is over. Then I have to put the second term, IR R drop and IR X drop. IR R drop, no? This is a resistive drop, always will have in phase with the current. So current is here, no? So IR drop is parallel to that one, which indicates that IR drop is in phase with the current, correct? Then the pending is Jx. J, the term indicates a 90 degree. So the inductive reactance is always having the 90 degree from the IR drop, correct? So that's what it is drawn, exactly 90 degree from IR drop. Then joining these three vectors. What are those vectors? VR, IR, IXL. Joining these three vectors or resultant of these three vectors will give you Vs vector. This is what we have formed as equation from the equivalent circuit diagram, correct? Now our aim is to find out performance parameters of the short transmission line. What are the performance parameters? Voltage regulation and efficiency. Generally we know regulation is nothing but the difference between the no load voltage and full load voltage and to full load voltage, correct? So whether it is a transformer or any machine, the no load voltage will be very high compared to that of the full load voltage. So it is it is the significance how the voltage is varied at the end while you vary the load, correct? So percentage regulation, whether it is a transformer or any machine, it is defined as the ratio of the difference between the no load and full load to the full load, correct? Now from the right angle triangle OCD, our aim is to find out, which is nothing but Vs minus VR divided by VR. This is our aim, correct? We are going to substitute everything. So for that, the right angle triangle, no, we will consider OCD. Where is OCD? See here, this is your O. This is your OCD. It's a right angle triangle, correct? In this right angle triangle, our aim is to find out Vs, okay? So this in OCD, no, using the Pythagoras theorem, OC square is equal to OD square plus CD square, correct? OD square plus CD square. This is the Pythagoras theorem, correct? OD is nothing but OE plus DE. The length of the DE, which is parallel to IR, no, the length of the DE is nothing but IR. So we know IR. And length of CB is IXL. Our aim is to find out the length of BD as well as length of OE. So consider the triangle, right angle triangle. This is your right angle triangle, correct? This is O, this is E in this triangle, and this is A. So this is enough. AE is equal to BD. So it's enough to find out AE and it's enough to find out OE. And we know this angle is phi r, correct? This angle is phi r. For our understanding, I'll put this as lowercase, okay? And this one is VR. Whenever you know hypotenuse, if you want to find out opposite side, means this will be VR sin phi r. This length is VR sin phi r. Whenever in a right angle triangle, if you want to find out this opposite and adjacent side, if you know hypotenuse, then the adjacent side, this one is VR cos phi r, okay? This is what I am going to substitute in the equation, okay? See here, OE is equal to VR cos phi r and ED is equal to IR, CB is equal to VR sin phi r, BD is equal to IXL the whole square. Correct? Then simplifying this, we will get this answer. And the same manner for leading type loads, no, this is actually plus. For lagging type loads it will be plus, for leading type it will be minus. Clear? So this will be minus. So combining together, no, for both leading and lagging, we will have this one plus minus. The plus sign is for lagging power factor load and minus sign for leading power factor load. Okay. Now if you do Vs minus Vr divided by Vr, we will get IR r cos phi r plus or minus IR x sin phi r divided by Vr. This is a voltage regulation formula for short transmission line. Similarly, transmission efficiency, another performance parameters. Correct? Here in efficiency, we already know it is generally output power divided by input power. Output power here is nothing but load side power. Load side power is nothing but receiving end power, VR IR cos phi r. Input power is nothing but sending end side, which is Vs Is cos phi s. So output we can write VR IR cos phi r. Input is nothing but input, we can write input is equal to output plus losses. Correct? Like that only it will be output plus losses. So the loss is I square R. So same thing, input is now, our input or sending end power is replaced by receiving end power plus loss multiplied by 100. This is the percentage of efficiency, transmission efficiency. Like this we can calculate the performance parameters of the line. Okay. Thank you all.